So our next speaker will be Sushant Agarwal. Will tell us about towards unification and robustness of post-hoc explanations.
Yeah, hi everyone. My name is Sushant Agarwal. That's how I look like without the mask. And this is actually my first in-person talk ever, so please be a little forgiving. And this work was done in collaboration with a bunch of Harvard people actually. So Shaheen Jabbari was a postdoc at Harvard. Chirag Agarwal was also a postdoc at Harvard. Sohini Upadhyay is a PhD student at Harvard. Stephen Wu is faculty at CMU, and Hima Lakkaraju is also faculty at Harvard. Okay, so this talk is about explainability. So we basically we consider, okay, my mask. So we have this black box predictive model, and we want to explain the prediction of this black box model at a particular point. So this black box model could be something random, like this complex and deep neural network. And we consider post hoc explanations that explain the prediction of this black box model at a given point. So two broad categories of techniques are perturbation-based techniques, such as LIME and SHAP, and gradient-based techniques, such as SmoothGrad and integrated gradients. In literature so far, they have usually been studied separately with like no clear connections. In this work, we actually make like the first attempt at establishing connections between these two broad families of explanation methods. And also research so far has mainly focused on empirical evaluation of explanation techniques. So we actually theoretically analyze two particular explanation techniques here. Sorry. Okay, so a little bit about the setup. So the black box complex model that we consider is a function f from Rd to R for D some natural number. And this is actually a pretty broad setting because it can clearly capture regression, and it can also capture binary or multi-class classification in the sense that the probability of belonging to a particular class can be thought of as f of x. And there's a different f for each class. So the methods that we consider here are also fall under the broad umbrella of feature attribution methods. So what feature attribution methods are? They're actually post hoc methods. So as you saw in the previous slide, we actually explain the prediction of a black box model f at a given point after the prediction has been made. And so what feature attribution methods actually do is they assign a score, or an importance or relevance score to each feature of x, and this score basically conveys how important this particular feature was in that particular prediction. And in this work, we look at two post hoc attribution methods, two post hoc explanation methods, that SmoothGrad and LIME. So SmoothGrad is a gradient-based method, and LIME is a perturbation-based method, and both of these also fall under the broad umbrella of feature attribution. Okay, just a summary of the contributions. So in this work, we theoretically analyze both SmoothGrad and LIME. So in particular, we derive explicit closed form expressions for the expected output values of the output explanations for SmoothGrad and LIME. And we actually observe something pretty surprising, or maybe not that surprising, that they actually converge to exactly the same value. So even though they come from two different families of explanations, and these two families are studied very separately in literature, we show that they actually converge to the same value. And the second contribution is we actually prove robustness properties for both SmoothGrad and LIME. So there have been many works in literature basically showing empirically and also theoretically recently that many explanation methods are non-robust, in the sense that you have two very nearby points with very similar labels, you would expect that their explanations are also very similar, but that doesn't hold. So in the sense, so many explanation methods are non-robust in this sense, and we actually show that both SmoothGrad and Lime are actually robust. Then we also show that both of them satisfy some additional nice properties such as linearity and proportionality that I will describe later. And the previous results, which I stated, actually hold for the expected value. So we, apart from that, we provide like a finite sample complexity analysis also. And finally, we, apart from the theoretical contributions, we have empirical experiments to validate the theory. Okay, so I'll briefly go over SmoothGrad, which was introduced in this paper by Smilkov and other people. So vanilla-based, so the most simple or vanilla gradient-based explanations basically compute the derivative of f at a particular point, and they return this derivative as the explanation. So the idea is that this derivative is a feature attribution method, and the idea is that the magnitude of the partial derivative with respect to a particular feature corresponds to the importance of that feature for that particular prediction. And it has been observed in practice that this simple gradient-based method, like just returning the gradient at a particular point, is often noisy. So as you can see in the second picture, the heat map, this is actually the gradient, is actually noisy, and it actually kind of highlights random features and ignores important ones. So SmoothGrad was proposed as a solution, and what it basically does is instead of returning the gradient at a particular point x, it takes neighbors of that, it takes like neighboring points, a bunch of neighboring points in the local neighborhood of x, and it computes the gradient at each of these points, and it returns the average of these points. So it has been shown that in practice, SmoothGrad actually leads to sharper and like more accurate explanations. So a bit more formally about SmoothGrad. So let S be a set of input points, input data points in the neighborhood of X, which is the point you want to explain. So the explanation output by SmoothGrad is given by the following expression, where we basically sum up, average the gradients of each point in S. And when S is sampled from a distribution P, the expected output of SmoothGrad is given by the next expression, which is basically replacing the sample average with the expected value. Yeah.
Can you give just a little more intuition about how I should think about S? Like, is
Okay, so sure.
no perturbations on X? Or
Okay, maybe I could go
some
with
other set.
Okay, so is there a pointer?
Is there a pointer? I think the answer is no.
You can use the one.
Well,
that
there's
doesn't
something there.
count.
Yeah, you can use the mouse on your computer. Right.
Oh yeah, okay. Okay, so this is a different figure. Oh, I could actually use the board. So let's say we are in this, I don't know, domain space, and we want to explain the prediction at this particular point. So what the standard gradient-based method would do would basically compute the derivative. So we have this black box model F, and this is the point X. So the standard gradient-based method would actually just return the gradient of f of x. So basically, and what SmoothGrad does is basically samples some points in the local neighborhood of x. And how it does this in the paper at least is it samples it using a Gaussian distribution centered at x. And yeah, so basically points that are more closer to x actually get sampled more often because it's like a Gaussian distribution. Yeah, so and it basically samples a bunch of points and computes the gradient at each point, and then it averages it. Did I cover this? Yeah. Okay. Okay, so now I'll talk about the second explanation method that we talk about 10 minutes more. Okay. So this is called line. So what line basically does is it takes, like, as you can see in that figure, so the underlying function is actually like complex and like very nonlinear, but it takes, let's say we want to explain like the bright red point here, which my cursor is showing. So what it does is it basically approximates the decision boundary in the local neighborhood of that point by a linear function. So it learns a linear function that basically approximates the behavior of the black box model in like a small local neighborhood of X. And how it does this is basically it creates, like, again, like as in SmoothGrad, it creates perturbed samples in the local neighborhood of X, and it observes the prediction of the black box model F for these examples, and it fits a linear model to these labeled examples. So little more formally, so let S again denote the set of inputs in a local neighborhood of X. So the explanation of line can be written with the following expression, where we basically fit a linear function to the sample S via a least squares regression. And when S, the sample, is drawn from a distribution P, the expected output is given by the following expression, where we basically replace the sample empirical loss with the expected loss. Okay. So I come to the first main result in the paper. So as I also mentioned before, in response to the question, we need to choose like samples S in a local neighborhood of both the points. And the standard choice in practice is to actually sample this from a distribution P, where the distribution is said to be a Gaussian distribution centered at X with a covariance matrix sigma. And in practice, usually the covariance matrix sigma is an isotropic distribution, but our results hold for any covariance matrix sigma. So I'll briefly go over the theorem. So it basically says that given any black box function F and a data point to explain F, and let's say we choose the sample distribution to be a Gaussian distribution centered at X with covariance matrix sigma, where sigma is invertible, then the expected values of both SmoothGrad and line actually give the same output, and they're given by the following expression: sigma inverse covariance A comma F of A, where A is a random variable sampled from the distribution P, and covariance A F of A is basically a vector with the ith entry corresponding to the covariance of F of A and the ith coordinate of feature of A. And as I mentioned before, sigma is our results hold for any invertible sigma, but in practice, sigma is always said to be a diagonal matrix and almost always isotropic. So we note that if we look at this closed form a bit more carefully, it actually has a nice structure for a diagonal sigma. So remember that the feature attribution method basically returns a score for each feature. And in this case, the score of the ith feature will basically be a scalar times covariance of that feature with F of A. And in the case of an isotropic distribution, the scalar will be the same for each feature. Now we come to the second main result in this paper. So as I mentioned before, it has been shown that many explanation techniques are non-robust. So that basically means that given two very similar points, two very nearby points in the domain space, which also have very similar labels, the explanations at both the points could actually differ significantly. And this is like something we do not want. And so we actually show that both SmoothGrad and Lime avoid this non-robust behavior. And the notion of robustness we use is Lipschitz continuity, and actually global Lipschitz continuity. And the theorem is basically the following, that given a black box model whose gradient is bounded by, let's say, something, and the distribution is said to be this, then both SmoothGrad and Lime are L Lipschitz with this Lipschitz constant. And here I just put sigma to be an isotropic distribution, but because the Lipschitz constant looks nicer, but this robustness also holds for any general sigma. So apart from linearity, from robustness, we also show that both these we show that both SmoothGrad and Lime actually satisfy other desirable properties, which I'll go over here. So the first one is linearity, which basically states that if you have a complex function which can be written as the linear combination of two simpler functions, then the explanation of that function is also the same linear combination of the explanations of the two component functions. And so this is what we call linearity. And the second one is proportionality. So if the underlying function f is a linear function of this form, theta x plus b, where theta is the weight vector and b is the bias term, and we show that both SmoothGrad and Lime actually satisfy the property that the explanation output, which is a feature attribution vector, is a scalar multiple of the weight vector of the original linear function. And both these properties can be viewed as sanity checks for explanation methods, and also lend credibility to using both SmoothGrad and Lime as explanation methods. A negative consequence of proportionality is, though, that both SmoothGrad and Lime do not guarantee sparse explanations. So there have been many works actually trying to come up with sparse explanation methods. So that means that if there are, like, let's say, many features, you'd want the less important features to have weights, to have scores that like shrink towards zero if they're less important. And proportionality basically guarantees that if the underlying function is, let's say, linear and non-sparse, then the explanation will also be non-sparse. So negative result is that SmoothGrad and Lime do not result in sparse explanations. Just to summarize, also to note that apart from the results I stated above, which hold an expectation, we also provide like finite sample analysis for the number of samples required to converge to the expected value. And we have experiments to validate the theoretical results. And I'm done. Thank you.